Hey everyone, and welcome back to the channel. Today we are diving into a critical concept in system design, the single point of failure, or SPOF. Think of it as the Achilles heel of your system. One weak spot that can bring everything crashing down. So, a single point of failure is any component in your system whose failure can bring down the entire system. This can lead to downtime, potential data loss, and a lot of unhappy users also, and a loss in revenue. So let's try to make a simple example here. Let's say that imagine that we have a system with application servers, but only one load balancer. So let's say that we have a client, and the client sends a request through a load balancer, and the load balancer will distribute all these requests across the servers. Okay. In this scenario, the single load balancer is a single point of failure, because if it goes down, if this component goes down, even though you have healthy application servers, clients won't be able to reach them at all. The entire system becomes inaccessible. And our goal in system design is to minimize and ideally eliminate single point of failures to improve the overall reliability and availability of our system. So what is exactly a single point of failure? It's any component that lacks redundancy or backup. Think think back to our bridge analogy, if you know before. So basically, if a bridge is the only way to connect two cities, it's collapse, isolate them at all. Isolate them; they can't connect at all. So the bridge is a single point of failures, and in a distributed systems, failures are a fact of life. Hardware malfunctions, software bugs, power outages, network disruptions, even human error. They happen all the time. While we can't prevent every failure, we can design our system to withstand them without total collapse. So in system design, a single point of failure can be a single server, a network link, a database instance, a cache, or really any critical component without failover at all. Okay, let's make this example. Let's make another example. I guess it's similar to this one, and we will try to identify the single point of failures in this system. So let's say we have the client, and the client will send a request across a load balancer. The load balancer will distribute the request across our servers. Let's say that we have two servers right now to make this quite easy. And these servers will get data from our database server, let's say DB, and also they can get the data from a cache system as well. Okay, so here we have clients hitting a single load balancer which directs traffic to two application servers. These servers might pull the data from a single cache server, or if it's not there, from a single database. Let's talk about the load balancer. Let's in this design we have a few potential single point of failures. First, we have the load balancer here. As we discussed, if the single load balancer fails, all traffic stops. The fix for this one, we could add redundancy, so we could add another load balancer. It could be on a passive mode. So this will be LB2 and LB1. So this could be on a passive mode. So whenever our load balancer goes down, the other load balancer servers, which is in passive mode, can take over and start serving the clients and distribute the requests to the servers. Again, the fix for this one, we add a standby load balancer that can automatically take over if the primary one fails. Next one, we have here database. And with only one database, its failure means all your data is unavailable, leading to downtime and potentially data loss for this one. And the solution is to replicate our data. So we have one DB server. We can have like we can have another one, but I don't know how to where to put it. Let's make like we have another one DB server. We call it DB2, and we replicate the data to this server. So if this DB, let's call it DB2 from here. If this DB1 lost the data or it's not available at all, we still have DB2. So the solution for this one is data replication across multiple servers and location. And also we have the cache server. Now the cache server isn't a true single point of failure in that its failure won't bring down the entire system. However, when it's down, every request hits the database, significantly increasing its load and slowing down response time. So while not a system killer, it's still a point of concern. Okay, so notice that the application servers, which is S1 and S2, are not a single point of failure in this case because we have two of them. If one fails, the other one can still handle the load. Assuming the load balancer is configured correctly, this is the power of redundancy. So let's try. We need to understand how we identify these sneaky problems or these sneaky single point of failures. The first one, we have like something called map out the architecture. Basically, we create a detailed diagram of all of our components, services, and their dependencies, visually identify any single instances. Number two, we have dependency analysis. We understand how different services and components rely on each other. A single component required by many other without a backup is a red flag. Okay. Number three, failure impact assessment. We perform a what-if analysis for each component. We ask, what if this fails? If the answer is a catastrophic system failure or major degradation, it's likely a single point of failure. And lastly, chaos testing. This is a powerful technique where you intentionally inject failures into your systems to see how it behaves. Tools like Chaos Monkey can randomly shut down instances, relieve hidden single point of failures and weaknesses. Okay, now let's talk about the critical part, how to avoid these single point of failures. There are some strategies. First, we have redundancy. The most and effective approach. Have multiple instances of critical components that can take over if one fails. These can be active, like always running, or passive, which is to be standby or used only as a backup. Number two, load balancing. We'll distribute the incoming traffic across multiple healthy servers. Load balancers can detect failures and reroute traffic, preventing a single overloaded server from becoming a single point of failure. Number three, data replication. You basically copy your data to multiple locations. Synchronous replication will ensure real-time consistency, while asynchronous replication is more efficient but might have slight delay. Number four, we have geographic distribution. Deploy your services and data across multiple geographic regions. This protects against region outages. You can use like a content delivery network or CDN for global content distribution and consider multi-region cloud deployments. Number five, graceful handling of failures. Design your applications to handle failures without crashing. Implement the failover mechanisms to automatically switch to backup systems. For example, if a recommendation service fails, the core application should still function, perhaps with a temporary message. And number six, monitoring and alerts. Like proactive monitoring is a key to detect issue before they cause a major outages. Implement like health checks to automatically verify component status and set up automated alerts for any abnormal behavior. Ideally, aim for self-healing systems that can automatically recover from common failures, like auto-scaling to replace failed servers. Okay, identifying and implementing single point of failures is a fundamental aspect of building robust and reliable systems. By implementing redundancy, load balancing, data replication, and robust failure handling, you can significantly improve your system's resilience and keep those users happy. Yeah, that's it for this video. And if you like this video, please subscribe and hit the notification bell for more system design insights. And thanks for watching.